Welcome to this video on elastic potential energy and Hooke's law. We'll cover key concepts in GCSE Physics to help you master these topics for your exams. In this video, we'll explore what elastic potential energy is, examine Hooke's law, walk through a required practical, and share essential exam tips and equations. Elastic potential energy is stored energy found in objects that are stretched or compressed. When the deforming force is removed, this energy is released and can become kinetic energy. Let's begin our first chapter by looking closer at elastic potential energy and how it relates to deformation. Elastic potential energy is stored in various objects. Common examples in physics include springs, stretched elastic bands, and compressed objects like rubber balls or gas springs. When you apply force to a spring, it stretches. We measure this as extension, which is the increase in length from the spring's natural, unstretched state. Remember that extension is the change in length, not the total length. Always convert your measurements from centimeters to meters when using physics equations. There are three key quantities to know: force measured in newtons, extension measured in meters, and the spring constant, which is measured in newtons per meter. Moving on to Chapter 2, we will discuss Hooke's law and the relationship between force and extension. Hooke's law states that extension is directly proportional to the force applied, provided the limit of proportionality is not exceeded. Doubling the force doubles the extension. The equation is F equals K times E. F is force in newtons, K is the spring constant in newtons per meter, and E is extension in meters. The spring constant K represents stiffness. A higher K means a stiffer spring. In our example, a 10 Newton force applied to a 50 N per meter spring results in a 0.2 meter extension. Within the limit of proportionality, the graph is a straight line and Hooke's law applies. Beyond this point, the graph curves and the law no longer holds. Distinguishing between these regions is crucial for your exams. You need to know exactly when Hooke's law applies and when it breaks down. Finally, beyond the elastic limit, a material suffers permanent deformation and won't return to its original shape. Note that the elastic limit is very close to the limit of proportionality. It is important to understand the distinction between the limit of proportionality and the elastic limit. Beyond the limit of proportionality, Hooke's law is no longer valid, while exceeding the elastic limit results in permanent deformation. Now let's move on to Chapter 3, covering the required practical for investigating force and extension, including the methods and results. In this practical, you'll investigate how the extension of a spring changes when you apply different forces, allowing you to test Hooke's law and calculate the spring constant. For this experiment, you will need a steel spring, a clamp stand with a boss, a meter ruler, and a set of 100 grams masses to apply consistent increments of force. Follow these steps. Measure the natural length, add masses one by one, calculate the resulting extension, record your data in a table, and finally, plot a graph to find the line of best fit. Identify your variables clearly. The independent variable is the force, the dependent variable is the extension, and ensure your control variables like temperature and setup remain consistent. When recording results, organize them into a clear table with columns for mass, force, length, and extension. Remember to always include your units in the column headings. Moving to Chapter 4, we will focus on interpreting the force extension graph, which is a key part of analyzing your experimental data. Your graph should show a straight line passing through the origin if Hooke's law is obeyed. The gradient of this line tells you the spring constant, and any curvature indicates you've reached the limit of proportionality. A straight line through the origin confirms proportionality. The gradient equals the spring constant. A steeper gradient means a smaller spring constant, while a shallower one indicates a stiffer spring. Once the graph begins to curve, the spring has passed the limit of proportionality. If you keep increasing the force, you risk reaching the elastic limit and causing permanent damage to the spring. In Chapter 5, we look at elastic potential energy, which is the energy stored in a spring when it is stretched or compressed. When you stretch a spring, it stores elastic potential energy. Once the force is removed, this energy is typically transferred into kinetic energy as the spring returns to its original length. The formula is E equals a half times K times E squared. Be very careful to square the extension value before completing the calculation to avoid common exam mistakes. Let's walk through an example. If a spring with a constant of 40 N per meter is stretched by 0.05 meters, the stored elastic potential energy is calculated to be 0.05 joules. Let's look at the energy flow. When a force is applied, work is done to store energy in the spring's structure. Once released, that stored potential energy is transferred into kinetic energy. Moving to Chapter 6, we'll cover essential exam tips and point out common mistakes that often cost students marks. Being aware of these can make a huge difference. Common errors include dropping the half from the energy equation, using centimeters instead of meters, confusing total length with extension, or ignoring the limit of proportionality. Remember, Hooke's law only applies before the limit of proportionality is reached. If a question asks you to state the law, you must include this condition for full marks. Now let's test your knowledge with these 4 practice questions. Pause the video to try them out before moving to the solutions. Here are the answers to our practice questions. Check your calculations, ensure your units are correct, and review any areas where you might have slipped up. Here are your key equations at a glance. Remember, F equals K times E for force, and E subscript E equals half KE squared for energy. Units are just as important as the numbers themselves. Always use newtons for force, meters for extension, newtons per meter for the constant, and joules for energy. To recap, elastic energy is stored in deforming objects, Hooke's law requires proportionality, and always double-check your unit conversions and squaring in your energy calculations. You're all set. Keep revising, practicing your past papers, and remember to show you're working clearly. You have all the tools you need to succeed. Good luck!